Hello and welcome. In this module we will first review some basic concepts from electromagnetic theory which is required for us to study the wave propagation inside an optical fiber. Then we will look at behavior of this electromagnetic waves at boundaries. We will look at the phenomenon of total internal reflection which forms the basis for constructing optical waveguides. So, let us begin by talking about electromagnetic theory. We describe electromagnetic fields. There are 4 electromagnetic fields which are primary concern to us. These electromagnetic fields are called as electric field E, which is a function of both position in space as well as time in general. This electric field E is sometimes called as electric field intensity, and you have other field which is called as D, which is electric flux density, which will again be a function of both position as well as time. You have H, which is magnetic field or sometimes called as magnetic field intensity, which will also be functions of time. And finally, you have magnetic flux density, which is a function of both position as well as time. These quantities are functions of positions which are represented by vectors R, position vectors R, and at each position as well as with respect to time, these quantities change and these quantities are themselves vectors. Therefore, these are all called as vector fields. Okay. The source for these vector fields E, D, H and B are the charges and currents. The charges are specified as functions of position and they can also change with respect to time. So, if the amount of charge in a given region is changing, then it means that there will be some current flow that is happening. So, this charge density being a scalar quantity, we usually represent this one by the symbol rho, and the most general charge distribution that you can imagine is the volume charge density. This too will be a function of both space and time. However, this one is a scalar field. Why is this called a scalar field? Because at each position and at each time, the quantity that you get is a scalar. Charge density is a scalar, and you have another vector field. Okay. This vector field is the current density vector, which will also be a function of space and time. Now, for a long time it was thought that the electric phenomena which can be described by these quantities was kind of different from these 3 quantities which are closely associated with magnetic phenomena. So, for a long time people studied electric phenomena separately, magnetic phenomena separately, but then it was shown that these 2 phenomena are interrelated by experimental work of Faraday, and this complete electromagnetic model was given by Maxwell, building upon all earlier experimental researches in electricity and magnetism. So, today if we talk about electromagnetic theory or electromagnetic model, we start with Maxwell's equations which are applicable to all electromagnetic phenomena occurring at macroscopic scale, that is occurring at scales which are considerably larger than the atomic scales. Okay. And there is of course a corresponding theory for behavior of electrons and protons in terms of electromagnetic theory, but at those distances one has to supplement electromagnetic theory by quantum theory as well. However, for most macroscopic phenomena we study electromagnetic theory based on Maxwell's equations. Maxwell's equations, we customarily number them, there are 4 Maxwell's equations. These equations relate E, D, H, B. Okay. And there is one more equation which is the conservation of charge or the continuity of the current, which relates the 2 equations rho and J. Let me write down Maxwell's equations and I will briefly explain what these are. I would be unfortunately not able to completely talk about Maxwell equation or electromagnetic theory in detail because the scope of this course is not that much. However, there are excellent textbooks which talk about electromagnetic theory. At the end of this module, I would recommend 2 of them. You can look at those textbooks to fill in any gaps that we are going to introduce. As I said, there are 4 Maxwell's equations. There is no definite order to these equations. However, we write, this is my personal preference. So, I start with 2 curl equations and 2 divergence equations come later. So, the first curl equation is called as Faraday's law. It states that if you consider a loop or a conductor and there is a magnetic flux which is changing, magnetic flux being given by integral of the magnetic flux density. So, if this magnetic flux is changing with respect to time, okay, then there will be a EMF induced around the conductor, and this induced EMF is further related to this integral of E dot dl. The way I am writing these equations are what are called as differential forms. I will just write down the corresponding integral form for you guys to appreciate this law better. Okay. So, this integral of electric field, so there would be some electric field. Okay. This electric field, if you integrate, only the electric field component which is tangential to this loop will contribute to this integral, because this is a line integral around this particular path. So, if you look at this line integral of E, this gives you the EMF, and this EMF generated must be equal to total change or time rate of change of magnetic flux psi m, where magnetic flux is given by integrating the flux density vector over the surface which is bounded by this particular conducting loop. Alright. The second equation says very similar thing, except it applies to magnetic fields. Just as we have defined electromotive force or EMF, one can define MMF, okay, and this MMF is given by integral of H dot dl. If I am looking at a closed loop, then this would be the closed loop MMF. Okay. So, the corresponding quantity in the differential form is curl of H, or in the point form is curl of H. This was originally thought to be just the current density vector J. Okay. It was originally thought that this curl or the magnetomotive force MMF is only because of the current density J. However, later Maxwell added a very important term known as displacement current density. Okay. Displacement current density is the time rate of change of electric flux density D. D is the electric flux density. So, the time rate change of this flux density D, electric flux density D, will act like current, and it will continue the current wherever in those regions conduction current is not possible, conduction current being the J vector. Okay. There are two additional equations, one is del dot D equal to rho v. It simply says that the source for the D fields is the volume charge density, and you have the fourth equation which says that del dot B equal to 0. It does not mean that there is no source of magnetic fields, it just means that magnetic field lines or the magnetic flux lines B are occur in the closed loop configurations. There is no start or the end points, there is nothing like a magnetic charge, okay, which can generate magnetic fields, just like there is an electric charge. An electric charge will generate electric field lines, which if it is a positive charge, you would have seen that field lines are all drawn like coming out of that charge. If it is a negative charge, then the field lines would all be coming in. However, for the case of magnetic field lines, the sources are all currents, which means that the lines, the magnetic field lines will always be occurring in continuous loops. So, these are four Maxwell's equations. These Maxwell's equations have to be supplemented by a few additional relationships. These supplementary equations are normally the material descriptors, that is to say, if I consider a certain material medium, okay, and if I want to represent what is D here, what is E here, Maxwell's equation does not directly tell you that. Okay. Rather than that, this relationship must be given in terms of the constitutive parameters of the medium. So, these parameters are the permittivity epsilon and permeability mu, which relates D inside a material medium to electric field E, which relates B inside a material medium to field H. Okay. In the free space, of course, epsilon is equal to epsilon 0, mu is equal to mu 0. These are known as free space permittivity and free space permeability. Okay. Finally, there is also one important equation. This equation is called as the continuity equation. This continuity equation relates the charge density rho, or rather it relates the time rate of change of the charge density rho to the current density J. Okay. So, it means that in a closed loop, if you consider a closed surface, in this surface if the amount of charge is getting reduced, right, then obviously those charges must be coming out of the surface. So, if the charges come out of the surface, they would be constituting the current density J. Okay. So, it simply says that the amount of current that you are getting from a closed surface must be equal to the time rate of change of the charge density inside, or the time rate of change of the charge inside. Okay. So, these are Maxwell's equations. Now, we will look at the wave equation. Okay. We have already looked at wave equation in the previous module. So, we will not spend too much time there. I will just write down what is the wave equation. However, we will write down the solution of the wave equation and then examine what happens as these waves propagate and hit a particular boundary. Okay. So, we will see what happens to that case. The wave equation as derived in the previous module, you may want to check up on the previous module that we have derived, is obtained by first taking the curl of the Faraday's law and then invoking the second equation. Usually you are not applying these wave equations right at the source itself, you are applying at a region which is far away from the source. So, which means that you are applying them in the region where there are no sources, that is both the charge density rho as well as the current density vector J is equal to 0. So, the equations are considerably simplified. We will also assume that the medium is linear, homogeneous and isotropic. Okay. So, in such a medium B is equal to mu into H. So, I can write down in place of B, I can write down H, and since I am taking curl, I can interchange the del by del T operation and curl operation. Okay. Simplifying the left hand side, I get del square E, and the right hand side, or rather I should get minus del square E. The right hand side I will get as minus mu epsilon del square E by del T square. Cancelling off the minus and plus, I can remove this one. Okay. Now, one solution for this is to assume that waves are propagating along z direction. Okay. If the waves are propagating along z direction and we take only that Ex component is 0, then the solution for this one will be a wave whose electric field is a function of only z and time, and this electric field is given by some E0 which is the constant. So, we can maybe write down this as Eox, and then you have e to the power j omega t minus k into z, where we have assumed that this is a wave whose frequency is given by omega. So, this wave frequency is given by omega. This is angular frequency. So, this is radians per second. Okay. And then this k vector is related to omega for this case. It is given by k equals omega by Vp, where Vp is the phase velocity of the wave. Okay. It is the velocity with which the constant phase point for this plane wave would be propagating. So, Vp is equal to 1 by square root mu epsilon. For free space or vacuum, actually for free space or vacuum, in fact this phase velocity is equal to the speed of light, because mu will be equal to mu naught and epsilon is equal to epsilon naught. Okay. So, this of course is not the only way you can have a wave. In fact, you can have a wave along a particular direction which is described by the propagation vector k. Okay. In the previous case, the propagation vector was directed along the z axis, because I can write kz as k into z hat dot z into z hat. This k into z hat would have given me the vector k, right, and z into z hat is nothing but the position vector on a plane. Okay. So, the position vector is r. So, what you are doing is the dot product of k dot r, and wherever this k dot r is equal to some phi, and this phi is a constant, these are the constant phase planes. Okay. These constant phase planes in the case of this wave solution are plane. Okay. Moreover, in the plane which is z equal to constant, the orientation of the electric field. So, suppose this is the plane that I am considering, which is z equal to constant plane. Okay. In this, the orientation of the electric field will be along, say, x direction with a certain amplitude, and that amplitude does not change. So, the amplitude is essentially uniform over this plane. The corresponding H field will be H along y so that E cross H will point in the direction of the wave propagation or the energy propagation, and the amplitude of this magnetic field is actually reduced by a factor eta compared to the electric field. However, the frequency of this wave would be the same, and this wave also would be propagating along the z axis, in the sense that a complete electromagnetic wave or light, because we will consider light as electromagnetic wave, will be propagating along the z axis. It will have an electric field which is directed along the x axis, and the corresponding direction for the magnetic field is along y axis. So that x cross y will give you the direction of the wave propagation. Okay. Now, as I was saying, in general it is possible that the wave is propagating in any general axis. Okay. So, it might be propagating along a particular direction. So, we describe this direction by giving a direction vector, or we giving a propagation vector. Okay. This propagation vector I have indicated here in this diagram as k. Okay. And if I consider a plane, okay, if I consider a plane such that on this plane the position vector is given by r, then this k dot r represents all those points along which the phase is constant, and then we actually write down the electromagnetic wave on this plane by writing this as, so assuming that this electric field is directed along some direction E, okay, and has certain amplitude E0 and has a frequency omega. However, it is propagating in a general direction k, therefore, we write this as k dot r. Okay. As an example, consider wave which is propagating along the z and x plane. It is propagating at an angle of 45 degrees with respect to the z axis. Okay. So, what will be my k vector? K vector will be, assuming that the magnitude of the k vector is given by k, okay, the vector k will be given by magnitude of k times cos 45 degrees along z axis plus k sin 45 degrees along x axis, right. So, this is basically k by root 2 and x hat plus z hat. This describes the direction of wave propagation. This describes the direction of wave propagation. So, what would be the direction of the electric field? Well, the electric field has to be perpendicular to this one. So, because we are assuming plane waves, the electric field has to be perpendicular, and let us say this is the direction of the electric field. What will happen to the magnetic field? Well, magnetic field has to be perpendicular to both k vector as well as the E vector, that is both propagation direction as well as the electric field vector, in order to form a uniform plane wave. Okay. So, this particular wave, which is given by plane of constant phases in the form of a plane and a certain electric field which is perpendicular to k and uniform in that plane, and magnetic field which is perpendicular to both electric field and k vector, and it is also uniform in the plane, transverse plane, is called as transverse electromagnetic wave. Okay. So, this is called as transverse electromagnetic wave. So, this is the wave that would be described by, the electric field for such a wave can be described by this particular equation, where E will be the unit vector along the direction E, such that E is perpendicular to the direction for k. Okay. In our coordinate system, that is x and y coordinate system, this electric field E will have two components, right. What is the unit vector along E? It will have a component along minus z direction, because you can decompose this electric field into minus z and plus x component. Therefore, the unit vector along the electric field will be along minus z hat plus x hat. In this case, it kind of is 45 degrees, therefore, this would be 1 by root 2, but otherwise it will be a certain number. But the important point is the direction of the unit vector E is along x minus z hat by x minus z hat, that is the essential point. By root 2 is because we are assuming 45 degrees. Okay. So, this is all about uniform plane waves and they propagate. I understand that I have been rather quick in talking to you about these waves. Okay. However, as I said, the goal is to get to optical fiber propagation as soon as possible. So, we will stop this review of wave equation now and then talk about what happens when such a wave actually hits a particular boundary, that is it goes from one medium to an entirely different medium. So, you can imagine that there are 4 vector quantities or vector field quantities E, D, B and H, and we have to individually understand what happens when the electric field E of a certain wave or in a certain this one hits a boundary. Beyond this one, the entire region is characterized by certain parameters mu, epsilon and different mu, epsilon and sigma, which is the conductivity, and below this is characterized by mu, epsilon and sigma, which is different. So, you have a region 1. So, I am maybe not able to completely show you because my hand is kind of finite and limited, but you imagine that my hand is stretching all the way to infinity. Okay. So, it is like a plane which is stretching all the way to infinity, and there is an electric field which is propagating, okay, in some direction, does not matter, but the electric field E is in this direction. Okay. So, electric field E in region 1, which is satisfying Maxwell's equation, is given by this particular direction. Now, the question is what will happen to this electric field? So, if there is an electric field in this direction, arbitrarily I am taking it in the second region, is there a relationship between this electric field and this electric field? Similarly, is there a relationship between this D field and D field in the second region, right? Similarly, is there a relationship between B and H in one region to B and H in other region? So, in order to understand these relationships among these vector field quantities, it is necessary to briefly review the notion of boundary conditions. Boundary conditions come about in this way. There are 2 points, I have point 1, I have point 2, and these two should be joined by a straight line. Okay. Now, when I have a line, I actually also have a plane which separates these two, correct. So, I can actually have a plane which separates these two quantities. So, this is the notion of my plane which is separating point 1 and point 2. Point 1 is in region which is characterized by mu 1, epsilon 1 and if necessary sigma 1, which is the conductivity. Point 2 is in the region which is mu 2, epsilon 2 and sigma 2. There is an electric field here, let us say this is directed along this direction, and there is an electric field which is directed along this direction E1. Okay. Now, these are shown to be very far away from the two boundaries, but what we are interested is what happens as this electric field approaches this boundary, right. So, at this point what would be the electric field? It would be parallel, or it would actually be the same electric field E1 which I have written. So, this is the point 1 I am considering. For simplicity's sake, I started by showing points which are far away, but I want to understand what is happening on the boundary. Therefore, I will consider these points as close to the boundary as possible. What will happen to the electric field E2? The electric field E2 will also come out in this particular direction. Okay. Now, is there a relationship between E1 and E2? First, observe, this electric field can be written down in terms of its tangential and normal components, right. Similarly, this can be written in terms of its, let me try and write down this way. So, this can be written in terms of its tangential and normal components. Now, one of the equations that we have at our hand is the equation which says integral of E dot dl is equal to minus del magnetic field by del t, right. So, this is the equation that I have. Unfortunately, if you look back at Maxwell's equation, this is the only equation that I have for electric field E. So, whatever I have to do, I have to use only this equation to understand how the total electric field is changing. Now, that problem is not very obvious at all, because now let us try and evaluate this equation to the points which are separated by the boundary. Let us redraw this boundary situation that we have. This is the boundary that I have. So, I am going to assume a loop whose height is very small, although I am showing that this height is pretty large. Okay. Again, I made a mistake, this height should have been symmetrical, but anyway, it does not really matter. Okay. So, this height is h by 2, here is also h by 2, h by 2, h by 2, the length of this loop is L. Okay. Right. So, this is the region 1, this is region 2. Now, if you apply electric field E dot dl expression to this one, okay, if you apply that condition, what you have is you had an electric field which was directed in this way, right. So, you resolved this into two parts, that is normal and tangential. And while going around this loop, let us pick a direction for the loop. Let us say the loop is to be traversed in this particular way. Okay. So, as I am going through this loop, this portion of the loop lies in region 1, this portion of the loop lies in region 2. So, there are two portions which are lying. So, you can label these segments as 1, 2, 3 and 4 segments. Okay. So, what is the left hand side when you evaluate to the segment 1? Well, whatever the tangential component that you have obtained, which let us call it as ET1 times L, will be the result of the first segment. The integral of electric field on this line will be ET1 into L. What can you say about the integral along segment 2? Well, integral along segment 2 has to be broken up into two quantities. Here you have En1 h by 2, okay, and on top here you will have En2 h by 2. However, what is the component at this stage, at this segment, 4th segment? It is minus En1 h by 2, because these two are in the opposite directions, right, and the electric field along this segment, half of the segment as well as this half of the segment are the same. So, these two will cancel with each other and we do not really have to worry about the segments 2 and 4. For a similar reason, electric field here will be En2, the direction will be En2 h by 2, or the component will be En2 h by 2. Here you have electric field En2, however, this En2 into h by 2 will cancel with this other En2 into h by 2. Okay. So, you do not have to worry about the segments, the vertical segments, look at only the horizontal segment. For the horizontal segment, you have the contribution from the third segment as ET2, because it is the tangential component of the electric field in region 2 times L. This is the left hand side. What would be the right hand side? Let us keep this minus del by del t as it is and realize that this magnetic flux density is given by integral of B dot ds. Assuming that this loop is uniform and the magnetic field is uniform, what you get is the component of B times the area is given by L into h, and let us assume that it is only the normal component of the B that is contributing to the right hand side. Now, you look at left hand side and the right hand side. Okay, so, you have ET1 minus ET2 into L is equal to this one, L cancels on both sides. Now, what we do is we reduce the height of this loop, we take limit of h going to 0, and because Bn has to be finite, it is a field quantity which has to be finite, this entire right hand side goes to 0, and what you end up is having ET1 equal to ET2 across any two regions. Similarly, you can show that the normal component dN1 minus dN2 should be equal to the surface charge density that would exist if at all the medium is dielectric and not. You similarly have Ht1 minus Ht2 is equal to the surface current density or the sheet current density, and finally you have Bn1 minus Bn2 is equal to 0. We will stop here and look at the reflection and transmission of the waves in the next module. Thank you very much.